Hi, Algebra 2. So in this video, we're going to talk about some exponential models. We are going to end up doing some problems in our binder with our calculator, but first we have a little bit of notes for your notebook or a blank sheet of paper that you can add to your binder. And so we're really going to talk about exponential growth and exponential decay. And in terms of problems in real life, right? Like where some sort of population or value of a bank account or anything that grows in an exponential manner or decays. And so words we're going to be looking for growth would be growing, increasing. The word appreciates means like increases in value. Or if it's going to be a decay problem, we'll look for things like decaying or decreasing or depreciates. And so with these problems, we'll be usually given a rate. So given a rate as a percent, we have to change it to a decimal. Okay, so just like you've done in the past, if I gave you like 14%, you would change it to, you move the decimal place 1, 2 to the left, or divide by 100, and that would be 0.14. Or if I gave you 3.7%, again, you move that decimal 2 to the left, and that would give you 0.037, right? So we're going to need to change it to a decimal. And then we have this idea of if we're growing, basically you're keeping the initial amount, and then you're adding on, let's say 14%, if we were growing at 14%. And so when we are thinking about what we multiply by, what the base is, we have to actually add 1 to it, because that 1 counts as our like initial amount, and that we keep, right? So for growth, let's add this in blue here, growth. Okay, and this is maybe the most important part. My value of b in the equation, remember good old y equals ab to the x, my base, my multiplication factor is going to be 1 plus the rate. So if it was 14%, it would be 1 plus 0.14. Decay would be b equals, we're losing an amount from the initial amount we started. So if we're losing 14%, it would be 1 minus that rate. Okay, so that's how we're going to calculate our base. And so let's do a couple quick examples here. If I were telling you it was an 8% growth rate, we would say that our b value is going to be 1 plus, because it's growth, 0.08. And so that would be b equals 1.08, right? Because we're increasing by 8%. If it was a 12.5% depreciation, now we know we're decreasing, so my b value would be 1 minus, and I'm going to turn this into a decimal, 0.125, and so that would be b equals 0.875. All right, the other thing sometimes you'll have to do is, if I gave you an equation here, here's our a, b to the x, I can see that b equals 0.93, and so then if I ask you for the rate, I want to know what that r value is. What did we add or subtract from 1? And so basically you're kind of answering the question, how far from 1? Right? If it's growth, it would be how much above 1. If it's decay, how much below 1. Well, this would, so 1, you could just do the subtraction. 1 minus 0.93 would be 0.07. So 0.07, and so then I could say that r equals 0.07 or 7%. Okay, so now if you guys could pause the video, take out your binders and a calculator, and turn to page 349. All right, so here we are on page 349, and we're told the value of a car in thousands of dollars can be approximated by the model f of t equals 25 times 0.85 to the t, where t is the number of years since the car was new. So we have the value in thousands of dollars, and the number of years since the car was new is t. So tell whether the model represents exponential growth or exponential decay. So I'm going to look at B, which is right there. Since it's below 1, this is decay, since B is less than 1. Identify the annual percent increase or decrease. We know it's now going to be decrease because it's decay in value of the car. Right? That's what happens with a car, right? It decreases in value after you, as you own it. Okay. So here, that's what we looked at in that last one. It's how far from 1? Is B. And so you could, if you need to do the math, you can go ahead and you go like 1 minus 0.85. You can see it's 0.115. You might be able to do that in your head. And so it does say annual percent. So we do have to change this to a percent. So that would be 15% decrease annually. Every year it's going to lose 15% of its value. Estimate when the value of the car will be $8,000. Okay, so this is, I'm trying to find when, so I'm trying to, t equals what? I'm trying to solve for t. So I have to set up this equation. I'm going to be plugging in 8,000 as the f of t, the value. But notice that it's in thousands of dollars. So like, remember our 25, that's representing the initial value. It's the y-intercept. So $25,000 initial value. Right, y equals a, b to the x. A is the initial value, that y-intercept. So when the car was brand new, it was 25,000. Notice it's just 25 in the equation. So 8,000, I'm going to mark in the equation as 8. So 8 equals 25 times 0.85 to the t. Now, we don't have the algebra tools yet to solve this equation, but we do have our inspires, and we can use them to help us graph this and figure out where how many years it would take. We could kind of start plugging in values of t to kind of guess and check, but let's take a look at our inspire. So open your inspire to a graphs page. Right, and we're gonna just, I've got some screenshots we can look at over here. So to start, you've got your graphs page. You're gonna type in our function here, the 25 times 0.85 to the x. The calculator, you gotta use x, f1 of x. So you take your t, turn it into an x. It won't work if you use t. So there, we type that in. Hit enter, and when you do that, this pops up. We can only see a little sliver of the graph there, so we're gonna have to change the window. And so to do that, what you're gonna do is you're gonna take your cursor, move it up to that 6.67, because I can tell it's the exponential graph is gonna be up higher, and we know the initial value is 25. That's the y-intercept. So I want you to take that your cursor over the 6.67, and you click the middle button twice. It's kind of like double clicking it, and it's now highlighted, and you can just type in a number bigger than 25. I went with 40. I think 40 is a good choice there. So type in 40 and then hit enter. And there, now we have a nice, better look at this function, this exponential decay function. All right, there's its y-intercept at 25. My job is to figure out where does it equal 8. Well, I can look at these tick marks, 2, 4, 6, 8, so it's there-ish, but what if we graphed the equation y equals 8, the line, the horizontal line y equals 8. So that's what you're going to do next. You're going to hit tab, press tab on your calculator, and that's going to bring up a second equation line. Okay, and so there you can see that second equation line, F2 comes up, type in 8, and then hit enter. And it graphs y equals 8 for us. There's that horizontal line. Now we can actually see where they cross. We could kind of estimate. We can see that it's pretty close to 1, 2, 3, 4, 6, 7 is where they cross. Real close to 7. But, so if like truly wanted an estimation, we could say about about t equals 7. But let's actually find the calculator can actually find the intersection point. So you're going to press menu now. So let's get rid of tab. You're going to press menu. Here's my marker. Menu. Press menu. And then you're going to look for analyze graph. And then you're going to look for intersection. And so there we go. Menu brings up this. 6 is analyze graph. 4 is intersection. Click on intersection. And let's see what happens. So you get this vertical dotted line, right? And what you can slide it left and right by just sliding back and forth with your finger. So you want to bring it somewhere to the left of that actual intersection point, and then you click the middle button to like lock it in place. And now you can drag to the right, slide to the right, and move it past the intersection point, and you'll see this intersection pop up, and you click again. And it sort of locks in that intersection point. So now we can see that it actually happens at 7.01109, 8. You might have fewer decimals, that's okay. So we know it's about 7 years, but we can actually now say that estimate when the value of the car will be $8,000. And we can say when t equals 7.01, or about 7 years. So in the second part there, what if the value of the car can be approximated by the model 25 times 0.9 to the t? So instead of 0.85, the base is 0.9. So now we're just losing 10% per year. I guess I answered the first part of the question there. If it's 0.9, if base is 0.9, then I know that I could do 1 minus 0.9, and that's going to give me 0.1, and that's my rate. But if I want it as a decimal, that would be 10% per year decrease. And then estimate so that's the first part of this answer, and estimate the value of the car will be $8,000. So we're going to solve that same equation again, except now it's 8 equals 25 times 0.9 to the t. So you try that again with your calculator. I would open a new calculator page, and then type in the new equation, type in 8 again, see if you can find that intersection point. So pause the video, try that out. Alright, let's see how you did. You should end up with t is about equal to 10.8146, or about 10.8 years. I'm good with 1 decimal place there. Alright, I'm going to continue on and explain and talk through number 2. If you think you've got it and you want to pause the video and kind of try 2 on your own first, you can. Otherwise, let's kind of move on to that now. So in 2000, the world population was about 6.09 billion. And during the next 13 years, the world population increased by about 1.18% each year. So part A, write an exponential growth model giving the population in billions of years after 2000. So t represents the number of years after 2000, and then estimate the world population in 2005. So let's see, I'm trying to write f of t equals ab to the t, and I am given an initial amount, right? There's my initial amount. So that, if you remember, goes in A. So I already know that this is going to be 6.09 for A, and then I just have to figure out B. And I know B is going to be my 1, and since this is increasing, plus the rate. Well, my rate is 1.18%, which as a decimal, 0.0118. So 1 plus 0.0118 or 1.0118. And because, I mean, think about this. This is billions of people. So those decimals, we want to be as accurate as possible. So we got to keep all those decimals there. 0.0118 is my base there. And so there's my model, f of t. If I plug in t, that's going to estimate the number of years. So, or estimate the population based on the number of years. So part 2 of that problem there said estimate in 2005. Well, that's 5 years after 2000, so I'm going to plug in 5 for t. So I would say, I would say f of 5 equals 6.09 times 1.0118 to the 5. Go ahead and type that in your calculator, and you should get 6.45789. Oh, look at that. 789. And so let's call that about 6.5 billion. 2 decimals seems appropriate here because these are billions. So we would say 6.46 about billion people. Part B, estimate the year when the world population was 7 billion. So here, now I know the population. That's the f of t part. So that would be 7 equals 6.09, 1.0118 to the t. Remember, you're going to graph f1 of x equals 6.09 times 1.0118 to the t. You're going to graph f2 of x equals 7, and then find the intersection. And when you do that, you get t is about equal to 11.87. And so estimate the year when the world population was 7 billion. Well, 11 would be 2011. And so at the end of 2011, so I would say 2012. I'd round up to the next year there. Assume the world population increased by 1.5% each year. Write an equation to model the situation. Okay, so that just means my b is now 1 plus 0.015. I changed 1.5% to a decimal. And so now my model would be f of t equals 6.09 times 1.015 to the t. And then let's see how, like, not much bigger, 1.18% versus 1.15%. So a little bit faster rate. Let's see how big of a difference that makes. Estimate the year when the population was 7 billion. So we solve that equation now. 7 equals 6.09, 1.015 to the t. Do your graphing. Pause the video. And we find that we get t equals about 9.3536. So 2009 to 2010, somewhere in between there. Right, like early 2009 is when it would hit 7 billion. Okay. We are going to practice this some more, but hopefully this video gives you a good start here, and thanks for watching.